An alkene has a carbon-carbon double bond. It has the general formula CXH2X. So if I have 5 carbons, I have 10 hydrogens. If I have 3 carbons, I have 6 hydrogens. The location of the double bond is always indicated by the lowest numbered carbon atom involved in the bond. So if I wanted propene, I would have that. If I wanted 2-propene, then I would have this one, because the second carbon is the lowest numbered carbon in the bond. When naming alkenes, they always end in E and E. Aromatic hydrocarbons are cyclic unsaturated hydrocarbons. They usually have a smell, and the simplest is benzene. It's very stable and it undergoes substitution reactions like the alkanes. If benzene, which is shown here, is acting as a substituent, then it would be called phenyl. Benzene is a 6-carbon ring with double bonds alternating every other bond. You can draw it like this, but if so, then you would need to draw it both structures because it displays resonance. Or you can draw it like a hexagon with a circle in the middle, showing that that double bond is spread throughout. With cyclic alkenes, when numbering carbons, you should number through the double bond towards the substituent. And here's another picture of benzene showing the 2 ways that you can draw it. So if we are drawing for decene, the first thing you need to do, just like earlier, is decide how many carbons your longest chain is. Dec was 10, so we need 10 carbons. The 4th carbon should have a double bond because it ends in E and E. And now we just need to add our hydrogens. Be careful when you get to the double bond because it already has 3, it just needs 1. I'm going to pause the video and try the next one on your own. You have hex, which means we need 6 carbons. On the second carbon, we need a double bond. Also on the second carbon, we need a methyl group coming off, as well as the 3rd carbon. And now I need my hydrogens. If you caught that, I have too many hydrogens on that second carbon. So to always double check that each of your carbon only has 4 bonds attached to it. With double bonds, you have something called a Cis-Trans isomer. So when you have substituents on the same side of the double bond, we're going to designate that cis. If they're on opposite sides, it's designated trans. So this top one is a cis isomer because notice the CH3s are on the same side of the double bond. While trans, they're on opposite. Next time in class, we'll have some more practice on figuring out if they're cis or trans. Now, alkyne contains a carbon-carbon triple bond, and it ends in Y and E. Reactions involving alkenes and alkynes are hydrogenation, which is the addition of hydrogen to make an alkane, which is the opposite of dehydrogenation. In this case, we have a double or a triple bond, and hydrogen. That hydrogen breaks the double bond and saturates our alkene again. We're going to add a hydrogen on both sides of where the double bond was. Halogenation is just like hydrogenation, except instead of adding hydrogens, we're going to add halogens. And polymerization is the linking of many smaller molecules together. Those smaller molecules are referred to as monomers. So polymer is a long chain like molecule that's built from monomers. There's addition polymerization, in which case monomers add together and do not give any other products. And that would be like slime. We have condensation polymerization. When the two chains go together, there'll be a small molecule such as water given off. And that would be like nylon. When nylon's made, those two molecules go together to make water and the nylon chain. Two types of polymers you need to know are thermoset and thermoplastic. Thermoset, once it's set, it cannot be softened, dissolved, or melted again, while thermoplastic polymers can be remelted after it's been molded.